Alright, now having expressed my frustration with this particular portion of the text, continue on, and if you feel the same frustration as I did, maybe it's a good thing, maybe it's a blessing in disguise. Maybe it will motivate you to think harder about the interpretation of quantum mechanics. The formalism, I've said several times already, the formalism most people agree with. Quantum mechanics obviously works, right? Like for example, the previous previous chapter on scattering, we got some really accurate results that are confirmed by experimental results, right? So quantum mechanics obviously works. The theory is doing something right, but the interpretation of the theory, what it means, trying to visualize it, imagine what's going on, is very, very difficult. There's a consensus on the formalism, and there is no consensus on the interpretation of the formalism. I think that's a fair statement, right? So be confused in terms of interpreting what's going on here, right? Okay, so he's assuming, I think, after the fall of the trapdoor, so you get then a partitioning of your box into two volumes, say volume 1, volume 2, or volume A, volume B, same thing, right? And he assumes now that you can normalize the wave function that's in volume A, or volume 1, and separately normalize the wave function that's in volume 2, or volume B. And here, this I found very confusing. Anyway, so for volume A, this psi function here is your superposition, right? And so you're integrating now over the volume A, and that will give you C1 squared. And a similar statement, now you're integrating again your superposition psi over volume B, and that will give you C2 squared. Now the particle has to be either in volume A or volume B, because that's all the total volume there is, right? That's the box. The particle has to be in either A or B. So therefore, now this is the probability that it's in volume A, and this is the probability it's in volume B. So those two probabilities have to be 1, because that's all the volume there is. And the particle's in there somewhere, right? So C1 squared plus C2 squared has to be 1. Right? So it's saying here, the particle, PTL, particle, must be in either volume A or volume B. Now, from the previous session, we had the overlap integral, which was of this, and there were various constants in front. So for this case, for this box thought experiment, Gedunken experiment, this psi1, the integral of psi1 star psi2, that integral is called the overlap integral, because if you have an integral like this and it's non-zero, then presumably psi1 and psi2 overlap to some extent. They are non-zero. Psi1 and psi2 are non-zero at the same point that they overlap. All right. My interpretation of what they're trying to say was a kind of motivation to get you to this point, to be talking about the overlap integral, because he wants to use this concept of the overlap integral, because it's very important when you start talking about wave functions as vectors, right? So you in a sense, you're multiplying two wave functions here and then integrating them, and we'll be doing this a lot in the coming sessions, right? So just, even though the interpretation is difficult, don't worry about it too much, because it's really just a motivator for this. And we need this. It's important for, as you'll see fairly soon, in the next session or so, for motivating the use of talking about wave functions as vectors, right? So looking on the space of all, when I say space, I mean just the set. So the set of all possible wave functions, I can call that a space, and you're looking on wave functions as vectors, so you can talk about a vector space, which is translated means the set of all possible wave functions. I hope that's clear. All right. Okay. Now at the bottom here, he talks. Now, if you can do this for like two spaces, A and B, so you have one trapdoor. So imagine now you had n-1 trapdoors, and they all fall at the same time. And then you partition your box, the volume of your box, into n volumes. Right? So you'd have volume 1, volume 2, volume n. Right? So you could then superpose. So if you had psi I, this is pretty well in the text. So this made me suspicious that his psi I is a wave function that exists in volume I and takes 0 value everywhere else. Huh? Well, all right. It's a thought experiment. You can do odd things. Because he says, so if you now have n volumes in your box, it's been partitioned by n-1 trapdoors, presumably, then if you superpose all these wave functions, you'll get this superposed wave function psi, which takes this form. So it's a weighted, again, complex numbers, these CIs, and these are the n of them, n separate wave functions, right? And you multiply each one by a complex number, sum the whole thing, and that also will be a solution to your Schrödinger equation for the particle in the box. Psi. This is a superposed wave function. Right? Okay. Now we have a superposition of n wave functions. Before we just had two, volume A, volume B, or volume 1, volume 2. So now we have n. So if you normalize the whole thing, and assuming the psi I is non-zero only in the. I'm going to fall off the bed. I'm going to have to use my little stool, I think. Just a minute. But my head gets much lower. All right. So normalizing, as we did in the 2-volume case, you get the overlap integral again. But now little m and little n now can range between 1 and big N. Okay. Now, if you assume these wave functions are non-zero only in their little volume, so the psi I would be non-zero only in the ith volume and 0 in all the others, the other n-1 volumes, then it follows from the when you normalize the superposed wave function that these overlap integrals are 0 in the case when m and n are different. Right? When n is not equal to m, this overlap integral here is 0. Right? But when m and n are the same, then you get 1. Okay? That's I should didn't say the volume here I assume is the ith volume, so this would be volume 1, so volume A, and this would be volume 2. I don't think that was in the text actually. So not happy. So I assume this is the ith volume here that's missing on this integral, right? So when they're the same wave function, then normalizing over that volume, you get 1. All right. So if they're different.